We would like to thank Brilliant.org for sponsoring this lesson. Creating online content is enormously time-intensive, and we depend on our supporters and sponsors to help us continue. Brilliant is also dedicated to making education available to everyone by making interactive lessons interesting to learners of any age. The true genius of Brilliant are the hands-on problem-solving puzzles that make learning fun and intuitive, very different from what most of us had to endure in school. These can really help you remember what you study. I use these to help me brush up on fundamentals, like basic math and science, so I can progress through to the subjects I truly love, like logic, scientific thinking, gravitational physics, and special relativity. They also have great lessons on new frontiers in science, like neural networks, quantum computing, and yes, rocket science. These lessons have helped me visualize these complicated concepts, and if you would like to do the same, we can offer a discount. To get started for free, visit brilliant.org/Terran Space Academy or click on the link in the description. The first 200 of you will get 20% off Brilliant's annual premium subscription. The Academy will also receive some financial support from Brilliant, which we appreciate. You will find that when you are studying and learning just to better yourself, it brings a tremendous enjoyment to the process. And remember, a deep understanding of the basics is how we come to truly understand a complicated subject. Hello and welcome to the Terran Space Academy, where we help prepare you for a bright future in the space industry. Please don't forget to like and subscribe, and we appreciate your help on Patreon. Thank you. Today, let's look at designing our own rocket for a lunar mission and comparing our fuel choices. Where would we start? First, what is the mass you want to get into space, and where in space is it going? Let's look at the last question first. In general, remember the number 9.4 kilometers per second. This is a good delta V estimate to launch from the Earth. Subtracting the gravity drag and air resistance will get us to a low Earth orbit with an orbital velocity of about 7,800 meters per second. This would be an orbital altitude of about 170 kilometers. That's very low, and your spacecraft or satellite would experience a lot of atmospheric drag, but you don't have to stay there. Once in LEO, you can budget to go wherever you want, to a higher, more stable orbit, or elsewhere if you calculated enough delta V. There are also ways to increase delta V without burning more propellant. You might plan to launch your rocket from or near the equator, maybe to put multiple small Earth observation satellites into low Earth orbit. The European Space Agency has a launch site just 5 degrees north of the equator. Or you could launch from a ship, like the space company Sea Launch used to, using Ukrainian-built Zenit rockets. Here, the spin of the Earth to the east adds about 465 meters per second. So we could budget a little less than 9 kilometers per second delta V, or get more mass to orbit if we launched at the equator. The farther north or south from the equator you launch, the less effect the Earth's spin has on your velocity. If you need to get a large Earth observation satellite to a polar orbit, launching due south from Vandenberg Space Force Base, or perhaps due north from the European spaceport at Kourou, which will both keep your rocket from flying over inhabited areas. But you won't get any boost from the Earth's spin, so we're back up to about 9.4 kilometers per second. Once we are in low Earth orbit, we can make an inclination change, to change the angle from the equator that we are orbiting the Earth. To do that, we would need to budget the vector change in velocity between the two crossing points of the initial and final planes. This takes a lot of propellant, though, and we should try to avoid them by launching as close to our desired inclination as possible. If we launch from the Kennedy Space Center in Florida, which has a latitude of 28 degrees 36 minutes, we would need to burn about 4.24 kilometers per second of delta V to get into an equatorial orbit. If we had launched from the equator to start with, we wouldn't need to do that. To go from LEO to geosynchronous orbit adds about 4.33 kilometers per second. Getting to low lunar orbit would cost about 4.04 kilometers per second. Notice that it takes more delta V to get from a 28 degree inclination to the equator than it does to get from low Earth orbit to the Moon. That means orbital inclination changes are very expensive. It also takes more delta V to get into a stable geosynchronous orbit than to go onto the Moon, because of the delta V needed to circularize the geosynchronous orbit from the transfer orbit. If we add the delta V needed to get to LEO with that needed to get to the Moon, we get a total of about 13.44 kilometers or 13,440 meters per second. We also need to have a lunar orbit insertion burn. This requires a minimum of 680 meters per second or 0.68 kilometers per second of delta V. Apollo 11 needed 889 meters per second as they were coming in fast. This put them into a low lunar orbit with a 113 kilometer perisyntheon, not perigee, remember we are not orbiting the Earth, and a 313 kilometer aposyntheon. We'll use the Apollo numbers to be safe, and that brings us to 14,329 meters per second delta V. Landing on the Moon from low lunar orbit will cost you another 1.87 kilometers per second. That brings us to a total of 16,199 meters per second with some safety margins, and we'll round that to an even 16.2 kilometers per second. Getting back into low lunar orbit from the surface is the same. Going from the Moon back to the Earth is much easier than getting from the Earth to the Moon. That's because the gravitational hill is not nearly so steep on the way back. Once on the Moon, we will have our rover scoop up lunar regolith using neutron analysis to analyze the regolith for the scientists. We will discard large rocks after they've been analyzed, and we will end up with a very fine powder. This powder will then be loaded into a 3D printer designed to work in the Moon's lower gravity. Then we will 3D print some commemorative coins. Let's make that 100 coins at about 5 grams mass each, so 500 grams or half a kilogram to be returned to Earth. So we will put a lander on the lunar surface, where we will deploy a rover to explore the surroundings while sifting and analyzing regolith, positing the resultant powder into a 3D printer, which will make our mostly aluminum with a little titanium moon coins. Our rover will be powered by a next-generation radioisotope thermal generator, or RTG. This RTG will use innovative thermovoltaic technology explained in this lesson. This technology will soon change the world, making our power generation 2.5 times more efficient than older systems. We will still have solar panels for extra power, and we will use a radioactive element that decays over just a few years and generates lots of heat. Not the more expensive isotopes used by NASA. The heat generated by a decaying isotope is called the decay heat. Here is a pellet of plutonium-238 made for a NASA RTG, glowing from the heat produced. The old Soviet Lunokhod rovers used polonium-210 for heat. They didn't use it for power, using solar panels instead, as the heat-to-electricity fraction was too low to justify the mass back then. The heating unit wasn't very large at all, as you can see here. Polonium-210 decays to a stable isotope of lead with a half-life of 4.5 months. We could also use a spent fuel rod from a nuclear reactor. These put out about 500 watts of heat energy 5 years after their initial removal from the reactor. 300 years later, they would still be putting out about 85% of that. Now we are not creating more nuclear waste, but instead reusing what would be stored indefinitely on Earth. And while on our way to the Moon, we will deploy a 3-unit CubeSat to an L2 near rectilinear halo orbit, so we can explore the far side of the Moon like China is doing right now. Now let's work backwards. We will set a mass budget for our lander and rover of 200 kilograms. 100 for the lander with its own cameras and communications array, and 100 kilograms for the rover, which will analyze the lunar regolith samples and can travel great distances, communicating directly with the lander when possible and relaying through the CubeSat when necessary. The rover will be equipped with 4 high-resolution cameras, so that operators, scholars, and students back on Earth can put on VR goggles and see a panoramic view of the Moon around them. Now we have defined our mission, and again we can work backwards to see what our rocket needs to have. We have gone over our rocket equation many times, but let's review just a little. Delta V equals the exhaust velocity times the natural log of the initial mass over the final mass. And we rearrange this to say that the initial mass equals the final mass times e to the power of delta V over VE, or that the final mass equals the initial mass divided by e to the power of delta V over VE. Now just a few more equations. The exhaust velocity here can be calculated from the specific impulse, if we multiply the specific impulse by the force of gravity on Earth. The strength of Earth's gravitational field is an average of 9.807 meters per second squared. We need that here as 1g. Now we just need our specific impulse. But what will that be? To get the specific impulse, we must choose a propellant, because the specific impulse changes with each combination of fuel and oxidizer. Now let's look back to our lunar lander. We said 200 kilograms landed on the moon for the lander, and the rover with the 3D printer and return rocket. First, let's look at whether this is realistic with our return rocket size. If we want to get 500 grams off the moon, it will cost us 1,870 meters per second of delta V. To return from the low lunar orbit to the Earth, it takes only about another 1,000 meters per second of delta V. That's because once we get past L1, the Earth's gravity takes over and we fall to the Earth. Let's use a solid rocket motor with a specific impulse and vacuum of maybe 280 seconds. This would be a high-performing but realistic goal, and is achieved by the GEM solid rocket motors, using hydroxyl-terminated polybutadiene-bound ammonium perchlorate composite propellant. Adding our delta V to get off the moon and past L1 gives us 2,870 meters per second. Let's round that to 3 kilometers per second to have a safety margin. We turn 280 seconds into exit velocity and get about 2,746 meters per second VE. Now we take the mass of the coin, 0.5 kilograms, and let's add 4.5 kilograms for structural mass for the return rocket and entry capsule. That's a single-stage rocket with a total dry mass of 5 kilograms. Now we use our rocket equation to see that we would need about 15 kilograms of initial mass. That means 10 kilograms, or about 2/3 of our rocket, needs to be propellant. So let's make the rover 100 kilograms total, including the return rocket, and the lander with its communications array will be another 100 kilograms total. We'll have heating and energy rods on both the lander and the rover. The coins will be printed on the rover and dropped into the return rocket, and there we go. Now to land 200 kilograms safely on the moon would mean coming out of low lunar orbit with a delta V of 1,870 meters per second. If we put that into our equation to calculate initial mass, we need the specific impulse of our landing engines. Cryogenic hydrogen is a complicated fuel in some ways, but nothing beats the specific impulse. Let's use RL-10 liquid hydrogen and liquid oxygen engines for our lander. If we estimate a specific impulse of 450 seconds, we get an exit velocity of 4,413 meters per second. Now we need one more number. The constant E is 2.7183. Using these in our equation gives us a mass in low lunar orbit of 306 kilograms. Our lunar insertion burn was 889 meters per second. We'll round that up to 1,000 and calculate the mass that came from low Earth orbit on its way to the moon. That comes to 375 kilograms. We said that we needed 9,400 meters per second to fight gravity and aerodynamic drag and get to low Earth orbit, and another 4,040 meters per second to be on our way to the moon. We're going to use a propulsion module on the lunar spacecraft to get that 4,040 meters per second of delta V, using the hydrogen-based RL-10s again. If our propulsion module has a dry mass of 125 kilograms, this gives us a total mass of 500 kilograms. Using our initial mass version of the rocket equations again, we see that we would need to start with 1,248 kilograms in low Earth orbit, and let's round that up to 1,250 kilograms, and design a 2-stage launch vehicle to get this into low Earth orbit. If we use RP-1, we would have a specific impulse of about 282 to 311 seconds for the first stage, and about 348 seconds with a vacuum-optimized second-stage engine. We've seen numbers showing the dry mass of a Falcon 9 SpaceX Block 5 booster is between 22,200 and 25,600 kilograms, while the fueled mass of just the booster is between 421,300 and 433,100 kilograms. Let's go with 25,000 kilograms for the dry mass and 425,000 for the wet mass. That gives us a dry mass of almost exactly 5% of the total booster mass using RP-1. Since the Falcon 9 has the widest diameter that can navigate American roads, 3.7 meters, let's take a look at using the same dimensions with different fuels. The first stage uses 9 Merlin gas generator open-cycle rocket engines and is 41.2 meters tall. The interstage is 6.5 meters, and the second stage is 13.8 meters tall with an empty mass of 3,900 kilograms and a propellant mass of 92,670 kilograms, giving a total mass of 96,570 kilograms. The payload fairing is 13.1 meters tall, and all this adds up to 74.6 meters, but we know the Falcon 9 in cargo mode is about 70 meters tall. By cargo mode, I mean not carrying passengers in a Dragon capsule. Remember that the giant nozzle of the Merlin vacuum engine fits into the interstage and other parts fit together, which subtracts the extra 4.6 meters. But we could have also used an RS-68 or Raptor, giving us the option of hydrogen or methane fuel respectively. But if we're going to use hydrogen, we might as well use something much smaller, like an RL-10. And for the methane, we might use a methane-burning Pangea Aerospike, or the new M10 being built by Arianespace for the European Space Agency. Now we would have a complete rocket, and we can look at some comparisons. We can estimate the volume of the first stage tanks. A diameter of 3.7 meters gives us an area of 10.75 square meters. Times, say, 37 meters, taking some height off the bottom for the sea-level engines, and off the top for the avionics and battery pack. And we get 398 cubic meters of volume. We need to leave room for the helium pressure vessels, downcomer, and other structural components inside the tanks, including ullage. Ullage is the empty space in a tank left for gas. This gas needs to be pressurized to prevent vapor or vacuum lock. If we assume 38 cubic meters for all this, we get 360 cubic meters for propellant. A double check shows that would be 235 cubic meters of liquid oxygen and 125 cubic meters of RP1, which comes out about 294 and 105 metric tons each, which gives us a number very close to the known propellant mass. The second stage is about the same ratio, with the understanding that the oxygen-to-fuel ratio will be optimized for vacuum. So it might burn even more fuel-rich from stoichiometric than the first stage. Now let's take these volumes and modify them for different fuels. Using 2 or 3 RS-68s maybe for the hydrogen version first stage, and maybe a couple sea-level Raptor engines for the methane-fueled one. We have looked at fuels in this lesson, and that the oxidizer-to-fuel ratio is around 2.8 to 1 for the RP1 burning Merlin, 6 to 1 for the hydrogen-fueled RS-68, and 3.8 to 1 for the Raptor burning methane. If we do the math on these like we did in the previous lesson, we see that for the Falcon 9, the density of liquid oxygen is about 1,250 kilograms per cubic meter, while that of RP1 is about 840 kilograms per cubic meter. We said the oxidizer-to-fuel ratio for RP1 is about 2.8, so for every 1 kilogram of RP1, we need 2.8 kilograms of liquid oxygen. If 1 cubic meter of RP1 has a density of 840 kilograms, then for every 1 cubic meter of RP1, we need 2.352 kilograms of liquid oxygen. Since liquid oxygen has a density of 1,250 kilograms per cubic meter, for every 1 cubic meter of RP1, we would need 1.88 cubic meters of liquid oxygen. That means our turbo pump will need to move 1.88 times more liquid oxygen by volume than it will the RP1. This also means the tanks will be about 65% liquid oxygen by volume and 35% RP1. For hydrogen-fueled rockets, we can use the same calculation and see that about 75% of the available volume is liquid hydrogen fuel and 25% is liquid oxygen. That's because the density of the liquid hydrogen is extremely low compared to other fuels. For the methane, we get about 59% and 41%. Putting in the same volumes we use for the tanks gives us a hydrogen-fueled first stage with a propellant mass of less than 148 metric tons, and the second stage propellant mass would be a little more than 31 metric tons. The methane rocket would come out to 336.5 metric tons of propellant for the first stage, and 92.5 metric tons for the second stage. Now let's look at some delta V. Here we see the Falcon 9 with RP1, our hydrogen-fueled Falcon H, and a methane-fueled Falcon M. Here's the dry mass of the two stages, the mass of the fairings, interstage, and our payload to the moon. Here we see the specific impulse for these engines at sea level and in vacuum. Now let's see if any of these can get us to the moon. We will go all expendable. But let's also add the 4.04 kilometers per second to equal 13.44 kilometers per second. The total mass of our rockets is listed here. Here you can see the first burnout mass. That's the launch mass minus the propellant burned in the first stage. There's always some residual, non-burned propellant, but we'll ignore that for now. Now we can use the sea level specific impulse to calculate the delta V at first stage burnout. Then we get rid of the first stage dry mass and the interstage and fire the second stage engine. We burn all that fuel and calculate our delta V from the vacuum specific impulse. Then we get rid of the fairings and second stage. Now we have our lunar propulsion module and exploration system to head on to the moon. We see that using the Falcon 9 design, the best performance is from methane. The second best is RP1, and coming in last is the fuel with the highest efficiency, hydrogen. This exercise can help us understand why seemingly inefficient propellants like RP1 are still good to use. Now some will say this comparison isn't fair, because the rocket design is optimized for RP1, which still works well for methane, but would not be a great design for a hydrogen rocket, that needs much bigger tanks. But the point of the exercise is to show how fuel choices compare and can affect the Delta V. We also see that all of these rockets would get the job done. Now let's do something interesting. Let's use the methane-fueled Falcon 9 first stage with the hydrogen-fueled second stage. And here we see that we get better performance than all RP1 or all hydrogen, but still not as much as the all-methane rocket. I hope this helps explain why SpaceX is going all methane on the Starship instead of using methane and hydrogen like the New Glenn, and that this makes it easier for you to design your own rocket systems, and helps you understand the choices that aerospace companies have made. That's it for this lesson. A big thank you to all of our patrons, and stay safe at Astra Pro Terra.